Our speaker tonight is Dr. Itai Sfaradi, and he is currently a postdoctoral researcher in the Department of Astronomy at the University of California, Berkeley, right here in the best group. Part of my group. So he completed both his undergraduate and his graduate at the Hebrew University over in Jerusalem, and his research focuses on explosive astrophysical transients, particularly core collapse supernova and tidal disruption events, with a focus on observations in radio wavelengths, which he'll be telling us all about today. So please give a warm round of applause to our speaker.
Hi, everyone. First of all, you might hear my voice tremble a bit. I used to get anxious when I'm talking to a lot of people, and there are a lot of people here tonight. Also, feel free to ask questions throughout the entire night, throughout the entire talk. I don't mind that. Just raise your hand and ask a question. The talk is, as Daniel said, about radio observations. I'm conducting my research here, one floor above, doing radio observations of what we call astronomical transients. These are events that pass on short time scales, roughly days to weeks, months, and years. These are short time scales compared to time scales of the universe. Galaxies evolve on much longer time scales, on millions of years and even more. And these transients are faster. And there are three words that I want to emphasize in this title. First is stellar, which is star, explosion, and radio. And I'll focus the talk on what is a star. I'll start with basic description of a star and what's happening with it. Then, what do I mean by explosion? Why does the star explode? And what do I mean by stellar explosion? And the main focus will be what does radio has to do with it? Because I think some of you are either imagining Judy Foster in Contact, listening with headphones, or imagining the car radio being tuned to hear some music. This is not the case, so I'll try to make it a bit clearer. And let's start with what is a star. So the basic definition of a star, something like our sun, is a celestial, luminous, hot plasma that generates energy through nuclear fusion. That's the basic definition. But I like to think of stars as something that are basically a very massive object made of hot gas and balanced by two forces. We got gravity due to the high masses of the star, and we got the gravity tried to pull all the mass towards the center, and we got nuclear fusion happening at the center, generating energy, which holds the star against its own gravity. So there is this kind of balancing in a star between gravity and nuclear fusion, and for me, that's the basic picture. Now, what we are seeing in this picture, in this illustration, and in our sun, is the outermost layer of the star, what we call the photosphere. The star is made of different layers. We have the convective zones and radiative zones, which are different zones in which heat and radiation is transported. I don't care about that at all. What I care about is the core, because in the core you have enough pressure and enough, and the temperatures are high enough to generate nuclear fusion. And by nuclear fusion, I mean that you have a ball of gas made of mostly hydrogen, and in the center, hydrogen plus hydrogen fuse and generate a heavier element called helium and release the precious energy that we need to balance the star against its own gravity. But this is true for all stars, but massive stars are a bit different because this process doesn't stop here. For massive stars, which are at least 8 times the mass of our own sun, you'll get fusion of higher and higher elements. So as I said, helium, hydrogen plus hydrogen create helium. At some point, you have enough helium and the temperature and pressure are high enough. So you start fuse hydrogen plus hydrogen. So hydrogen and hydrogen fuse create carbon and again, releasing energies. And this process go on and on. You're going from the hydrogen to helium to carbon, oxygen, neon to over heavier and heavier elements until you get to an iron ash, which is the result of a silicon fusion. And you got this kind of very famous layer model. Some people call it onion layer model. And that's why I think that augurs are like massive stars. They have layers. They are made of layers of hydrogen, helium, carbon, and so on and so forth. And these layers are what building up our massive stars throughout its life. Now, I think that it's always important to discuss timescales when you discuss astronomical events, because timescales can be confusing when you think of astronomical timescales. And I'll start by saying that hydrogen burning, the phase of burning only hydrogen, happens on timescales of 7 million years for massive stars. Then helium starts to burn, and the burning of helium happens on a much faster timescales of few hundred thousand years. And as you go on to heavier and heavier elements, the process of burning these elements is getting shorter and shorter with time. So carbon burning happens on timescales of thousands of years, neon over the last year of evolution, and silicon burns on the last few days, even the last day of the star life. So what happens next? What happens after silicon is burning? So silicon is burning to create iron, and apparently because iron is very, very bound, is a very bound element, it cannot generate energy when it fuses. So this iron starts to build up at the core of the star and doesn't fuse. And if you remember the scenario that I described before, we need this fusion to hold the star against its own gravity. But iron doesn't fuse, so it doesn't release energy, and the star explodes. But what do I mean by explosion? So again, we have this kind of scenario of gravity and nuclear fusion playing together. At the point where you have enough iron to build up a massive core at the center of the star, nuclear fusion fails and gravity wins. When gravity wins, the iron core, basically the entire core contracts and implodes inwards, and the star, and at some point, somehow, we are not sure exactly how, the material is being bounced out and the star explodes as a supernova. So we have this scenario in which the star evolves, burn different elements throughout its life until it reaches an iron core. The iron can no longer support the star against its own gravity. The iron core contracts, implode, and the star explodes as a supernova. This is not a real video of a supernova. We can't see that, but this is something that will illustrate first how bright this event can be, and second, what happens because once the star explodes, once the iron core collapses and the star explodes, we get a very bright flash of light, and all the elements that are inside the stars are being ejected outside. They are now being freed to the universe. So if you think of it, all these elements that were fused at the center of the star are being expelled out and enrich our universe. Basically, the universe started only with hydrogen and helium. If you're familiar with this, this is the periodic table of the basic atoms that we know. The universe started with these two, mostly hydrogen, and all the other heavier elements needs different processes to create them. And here in green, you can see all the elements that are created by exploding massive stars. We talked about the carbon that is generated at the core, oxygen, neon, and we said that everything up to 26, which is iron, is being generated at the core, and you can see that iron is generated by exploding massive star. But you can also see that heavier elements are generated by exploding massive stars, and I told you that elements that the star generates only elements up to iron because iron cannot fuse, right? So apparently these elements are not created by the star itself. They are created by the explosion of the star. So once the star explodes, the pressure is high enough to create heavier elements than iron. And this is what we see here. Heavier elements than those are created in something called in something that is emerging neutron star binary. This is the focus of Daniel's talk. But this is not me. I'm mostly focused on that kind of event. Okay, so told you all this beautiful story of what we know so far, but how do we actually observe this? How do we actually see that? So for astronomers, everything boils down to the electromagnetic spectrum, and I think that everything basically boils down to the wavelengths of emission. So basically basically the visible light that you're seeing, that the stuff that you're seeing with our own eyes are just part of the electromagnetic spectrum. They are very small part of the electromagnetic spectrum, and they're focused on wavelength range of few hundred nanometers. This is very short wavelength range. But there are other wavelength ranges. So gamma rays and X-rays are much shorter in wavelengths. And the other side, which is the focus of this talk, which is radio wavelengths, are much longer wavelengths. And everything is basically the emission that we're seeing dependent on the wavelengths of the light. And we are seeing this emission with different telescopes and different wavelengths. For different wavelengths, you need to sometimes go to space. So this is the atmospheric opacity. So how much the atmosphere is opaque to us in that wavelength. So for gamma rays, X-rays, and ultraviolet light, you must go to space. You cannot see anything from Earth. Also for some of the infrared regimes. Visible light is mostly observed from the ground, but to get best results, you probably need to go to space. That's the atmosphere. But radio is why I think it's the coolest wavelength, is because it's basically the atmosphere is transparent to radio wavelengths. So you can do everything from ground. You don't need to go to space. You don't need to send out telescopes to space. And the even cooler part is that you can do it during the day. So we have to wait for the sun to go out and for you to go upstairs and see the stars. I'm actually observing stuff during the day. I don't care if the sun is up or not, as long as it's not on my line of sight. I can just observe my stuff during the day. So that's one cool thing about radio. So everything is boiling down to the wavelengths of the emission. Now, I can't really talk about transient without talking about the visible light. So I'll just show you that we are able to see these kinds of things in visible light, and then I'll move to what interests me. So this is a picture of a galaxy, roughly 20 million light years away, from May 16, 2023. And this is the same galaxy 4 days later. And if you turn on your astronomer eyes, you'll look at that point over here, and you'll see that it doesn't exist here. And this point here is what we believe is a supernova, and this supernova is called SN 2023 IXF. We are very creative with our names. SN means supernova, 2023 means it explodes in 2023, and IXF is just a serial number of this event. So you start counting from January 1st by the letter A, and then you go all the way up. So that supernova turned out to be in May, so it got the name IXF. And this is a very cool event because it's very nearby. You get this kind of nearby events only once every 10 years, roughly. And there is one astronomer from here, Nayana, that worked on the radio and X-ray observations of that event. She did a beautiful job at analyzing the radio and X-rays. The optical was done by another group. So they're a competitive group, but we care about the radio and X-ray, so we are cool with that. Cool. So we established the fact that we can see stuff in visible light. We established the fact that we believe that stuff are exploding, and we're seeing the light, the transient light during different days. But how do we observe with radio? So we observe with radio with radio dishes. So this is the radio dish from a telescope called the Very Large Array. Again, we are very creative with our names. The Very Large Array is a very large array of telescopes like that, exactly. Each telescope is 25 meters in diameter, and it collects all the light in radio wavelengths and focuses it here. And then the light travels here, and here you have different receivers which observe in different wavelengths of radio. So some wavelengths are centimeter wavelengths, and some are millimeter wavelengths, and that corresponds to different part of the radio spectrum. And we observe with this kind of telescopes. But as I said before, everything is about wavelengths, and for us astronomers, the bigger telescope you have, you manage to observe with bigger resolution. You manage to observe finer details in your field. And since the wavelengths of radio is very large, you need larger telescopes than you usually need in radio. Than you usually need in shorter wavelengths like optical. And it turns out that 25 meters is not enough. You need few miles of telescope in order to see fine details in your field. But engineerically, it's very hard to do that. It's very hard to build a very large telescope, which is a few miles apart. But luckily, we can do what we call interferometry, which is combining different dishes. So this is the VLA. This is actually an image from the Very Large Array in New Mexico. Beautiful place. If you haven't been there, I highly recommend. And we basically combine observations from different telescopes to simulate a bigger one. So each two telescopes are acting together, observing together at the same point in the sky. And they are effectively like one telescope with the size of the separation between them. So if you have two telescopes separated by a mile away, you effectively have one telescope with a diameter of 1 mile. And this array can actually move between different configurations. And this is the most compact configuration. The most extended configuration is where the maximum distance between two dishes is, I'm sorry, I'm not thinking in miles now. It's 36 kilometers, which I think is roughly 20 miles. So they are very distant apart. They're very far apart, and they know what each telescope is doing. And you can actually do it no matter where the telescopes are. And there is the effort called the Event Horizon Telescope, which locates different telescopes like that on different places on Earth, and all of them are acting together. So you have some telescopes here in the US, you have telescopes in Europe and in Chile, and all of them are acting together, and you have effectively a telescope that is the size of the Earth. And this is how we got the first picture of a black hole. This is a radio image of a black hole, the shadow that a black hole is creating in a neighboring galaxy. And this was done using this Event Horizon Telescope, combining different telescopes across all Earth. It's a great effort, a very difficult engineering process, but I think now we have two images of two different black holes. So it was worth it, in my opinion. Okay, so again, we established that we can actually see in radio light, in radio wavelengths, but what does the radio actually have to do with the exploding star? So why do we need the radio to observe the exploding star? So if you remember, I said that augurs are like massive stars. They have layers, but they also emit a lot of gas. Throughout their life, they will shed mass from their outer layers via stellar winds. So our sun also emits gas in stellar wind. These massive stars will also emit gas in stellar wind, and at different phases of the evolution. So remember, each phase of evolution is different phase of element burning. So different phases of evolution, the star can emit gas in different rates, in different velocities, in different masses. And here is something that I'm very proud of. Yeah.
Any questions?
Yeah.
So 7 million years, how come they're not all burned out?
So these are only massive stars, and massive stars actually live fast. They die fast. Less massive stars like our sun takes longer to burn.
They must be being formed as well.
Sorry?
So they must be being formed as
well. Yeah. Stars are being formed and exploding. So again, this is something that it's very basic, but I'm very proud of. This is the cross section of stars. So we're looking at a star from the side, and throughout its life, the star loses mass and emits mass in winds. And let's say 100,000 years before the explosion, it emits some gas, and then continuously it's emitting gas during this phase. It's during the helium burning phase, and then 1,000 years before the explosion, it emits gas during the carbon burning phase. 1 year before the explosion, it emits gas during the I think it was neon burning phase, but I'm not sure on that. And in the last few days before the explosion, it still emit gas and still emit stellar winds. And the key part here is that mass that was ejected from the star at earlier times before the explosion reaches distances that are greater than mass that was ejected right before the explosion. And that's what allows us to do basically to look back in time on stars with radio observations. Yeah.
What is the composition of the gas? Is it the same compound that's being burnt, or is it different?
So typically the outer layers are mostly hydrogen. Some stars shed their entire hydrogen envelope. But yeah, the outer layers are mostly hydrogen.
Okay, thank you.
Yeah.
How do you know the inner composition of the star?
Sorry?
How do you know what the inner composition is?
So after the star explodes, we are able to see different elements in the spectrum.
Yeah. Is there any relationship between an exploding star and what we see as a falling star here?
No. falling star is dust particles, small particles that burn in our atmosphere. These stars are far
Much further away.
much farther away. Yeah. So, as I said before, the radio emission is basically what helps us observe back in time in stars. And I'll try to explain that. So we had this kind of scenario of different layers deposited at different times before the explosion. Then we have the star exploding as a supernova. And this fast explosion generates a shock wave in the medium. This shock is very, very fast, a few percent of speed of light. And the key feature here is that it's faster than these winds. So it's moving faster than the winds that were ejected before the star explodes. And it reaches far distances, very fast. So within hours after the explosion, it already reached the matter that was deposited days before the explosion. Few weeks to months after the explosion, the shock wave reaches material that was deposited a year before the explosion. And as you continue, few years, roughly around a year after the explosion, you reach masses that were deposited 1,000 years before the explosion. And obviously, as you go on and on, the shock will eventually reach the very, very distant material. And this shock is what generating our radio emission. The interaction between the shock and the material outside is what's creating what we call synchrotron radiation. It's a relativistic radiation that generates radio emission. And the general picture is that the star exploded, there is a fast-moving shock wave propagating outwards, and this shock waves allows us to see backwards in time to different epochs of mass loss before the star exploded. This is the key feature of radio observations in core collapse supernovae. Yeah.
If the composition of emitter particles during this solar that close to when stars about to explode, are we pretty good at determining that stars will explode in the next 10 years or so?
So that's I think it's a bit difficult if you're searching at a distance because you don't see this kind of changes in single stars at a distance. If you know the star Betelgeuse, it is expected to explode as a supernova at some point, and the last few years there was some variation in the light from it, and people believe that it might be related to the final stages of its life, but it apparently wasn't. So it's hard to determine that, but we do see some stars that have precursor emission, so some emission which is different right before the explosion. Very few examples, and it needs to be very close by to see it. Yeah.
Is it the interacting gases from the shock wave and then the layers of gas that is emitted that create enough energy where those particles that emit?
Yeah, exactly. You get this shock wave is accelerating the electrons in the medium to relativistic velocities, and these relativistic velocities, when you have charge that is accelerating, it creates radiation, and this radiation is what we're seeing. Yeah.
What is the shock wave?
It's not a sound wave. It's sort of a sound wave, but it's just a disturbance in the medium. Yeah. It's different from shocks on Earth physically, but conceptually it's the same. Yeah.
What sort of the energy balance between at the time of explosion, the generation of photons coming out, the correct radiation, and the energy that goes into the shock wave?
Sorry, I don't think I understood that.
Of the total energy that's released during the explosion, some of it goes into the propagated shockwave.
Yeah.
And some of it is generated in
Yeah.
sonic emission and mass.
Okay. So a very small,
Three components, what's kind of the energy ratio?
so a very small fraction of the energy of the star is actually deposited in this outflow that is generating the shockwave. Most of the emission is in high energy particles. I'll continue, and I think we can continue later on with the questions. So to show you that I'm not lying, these are actually radio images of a supernova called SN 1993J. So it's exploded in 1993. And these are pictures, these are images taken in radio wavelengths, starting from here, going all the way that over 7 years. And you can see that it starts as a very small source on the sky. And as the shock propagates outwards, we're seeing the source getting larger. It's not that the source is getting closer to us, but the source is actually getting larger on the night sky. And we are able to see the outer regions of the shock. And we're actually able to measure the radius of this shock with time directly. So we actually can take from the center outside and measure what is the radius of the shock wave. I think this is probably the best radio image you can get in transient. Usually you get something like that is getting bright and then fade away. You don't see the structure because stuff are pretty distant and you don't have the resolution for that. But luckily in 1993, there was a very nearby event that said that we were able to study in radio, and I think this is one of the template radio supernovae that we use so far. Okay, so what happens after the star explodes? We said the star evolves, create different elements, explodes, but there is something that is left behind. So this something is typically either a black hole, compact object, which is either a black hole or a neutron star, which is left at the center. And we get these beautiful extended structures. This is the nebula supernova remnant called the Crab Nebula of supernova that exploded. I think it was the year 1054, if I remember correctly. And it was actually observed by I think it was Chinese astronomers back at that time. They saw a new light source on the sky. They didn't understand its nature, but there was a new light source, and they actually observed the explosion of this stuff. This is something that happened in our own galaxy. So we are able to see all the fine details of the explosion. We are able to see the fine details of the outer layers. This is a different nebula, which is a result of a different supernova, which I don't remember the name. Forgive me about that, but I do remember that this is an X-ray image. So this is an image taken in X-rays, not optical. And you're actually, if the sky will be nice to us, you'll actually see some of these. I think I don't know which exactly are going to see, but you are going to see some nebula. So you should ask some of the people that are going to be there when it exploded, and they probably won't know. Yeah. So far, I think I have time, right? Yeah. So far, I talked about the natural death of massive stars. This is the natural evolution, and this is their natural end. And you can think of it either as a natural death or heart attack that they get due to the iron core, which get them to die. But there are other ways to kill a star. Some of them are exciting, some of them are less. I'll start with what I think is the less exciting, but some people will disagree with me. So there is another scenario of a supernova in which you have a star that is called the white dwarf. It's a small star, so it's not a massive star, and a companion, which can be either another white dwarf or red supergiant with some other massive star. And the companion is feeding the star, is feeding the white dwarf until they reach the point where it cannot longer sustain itself, and it explodes as a supernova that we call supernova type 1A. This kind of supernova is actually not generating radio emission, so I don't think it's interesting, but don't tell the others. And this is a type 1A supernova. The other supernova that I talked about, the core collapse supernova, are usually are types. Their types is called either 1B, 1C, or type 2. And you can blame one of the astrophysicists here on that. Alex Lipyenko, I think he coined the term type 1 and type 2 supernovae, and we are stuck with that term since, which is not very informative. I prefer core collapse supernova or thermonuclear to this one, supernova. So that was one way to kill a star. The other way to kill a star is by a car accident or something like that. So this is actually what I'm focused on right now. This is my research. These events are called tidal disruption events. So in the center of each galaxy, you have a massive star, a supermassive black hole at the mass of at least million solar masses. And here is the view from the side of the supermassive black hole. This is supermassive black hole. We view the supermassive black hole from the side, and you'll start seeing a star that is very unfortunate. It's getting very close to it. And we'll zoom in a minute. Zoom out, sorry. And the star getting close to the supermassive black hole, getting stretched by the tidal forces that exert on it, like the tidal forces in the moon, and then get torn apart. Again, we are not seeing this with our own eyes. This is a simulation or artistic impression. But the end result is that you get fast outflows, very fast outflows that goes out. Roughly half of the star material is being ejected at high velocities outside, and half of it is accreted back to the supermassive black hole. And these fast outflows are what generating the radio emission. And in that case, we are not probing the star life before the explosion. What we are actually probing is the interaction between the shock and the environment. So we are probing the closest environment of the supermassive black hole. This kind of event can also generate jets, relativistic jets. So these are highly collimated outflows, which are bound to a cone-like shape at speeds that are near the speed of light. It's not shown here, but this is something that is of extreme interest to me. So I thought it's worth mentioning it. And I think the last case of killing a star that I want to show you is actually relating to Daniel research. When you have, I'll finish with that and that. When we have two neutron stars that are orbiting in a close orbit, they start to approach each other because they lose energy through gravitational waves. They lose energy through emitting gravitational waves. This is a prediction of the general relativity. They in spiral into one another, and at some point they collide and create what we call a kilonova. I think the name just came from a derivative of a supernova because we didn't know what is that exactly. I know that there was a debate whether to call it an hypernova or a kilonova, and the kilonova name is what people chose. And this event, we actually saw this kind of event only once, and it generated beautiful radio emission from the jetted relativistic outflow that was emitted from this event. So I think that if there is one thing that I want to emphasize is that there are many ways that you can kill a star. It can die by natural causes, or it can die by a car accident, or by just colliding with other stars. And we radio astronomers are kind of morbid. We really enjoy watching this happen, and we wait for that to happen. And just because we can actually probe the interaction of the star body with its environment. So it's kind of a nice probe of the environment and not of the event itself. So I'll finish here and I'll take questions now.